Okay, welcome everyone to today's ESC seminar. So this is the last one in this term series. Okay, my name's John Paul Latham and I'm reader in geomechanics here in ESC. I'm one of a team bringing you these lunchtime talks. Before welcoming our speaker, I'd like to point out to the attendees that they can participate through our Q&A session, which we'll be having after the talk. So on the right of your screen, you should see the Q&A icon with a question mark. That's the one you need to click, and then you can type in a question or a comment. So I'll be wrapping up the session at around 1, but we should have plenty of time for questions. So now for today's speaker, I'm very excited to be welcoming him. We have William Powrie. He's Professor of Geotechnical Engineering at the University of Southampton. So his main technical areas of expertise are in geotechnical aspects of transport infrastructure and sustainable waste and resource management. He was elected Fellow of the Royal Academy of Engineering in recognition of his work in these areas in 2009. And since then, he's ploughed vitally important new science territory in understanding and mitigating vegetation and climate change effects on our natural and engineered soil structures. He was principal investigator for Rail Research UK, that's 2003 to 2010. That was a universities-based Centre for Rail Systems Research, and now leads an EPSRC programme grant, which is called Track to the Future, which is aiming to provide the science needed to underpin a radical overhaul in techniques for railway track design, construction and maintenance. By the way, this sounds horrendously complex work, William, handling all the responses to train vibrations. Yes, major projects on which he has worked include the A55 Conway Crossing, the Jubilee Line extension stations at Canary Wharf and Canada Water, and HS1. He's currently working on the HS2 on geotechnical and earthworks aspects, and he's co-author of numerous industry and Syria guidelines and served as editor on several geotechnical journal titles. He led a major EPSRC funded program of fundamental research, science and strategies for management of residual wastes, with the aim of enabling and encouraging landfill operation so as to accelerate biodegradation and stabilization of the waste. And he was a co-author of the Institute of Wastes Management report on the role and operation of Flushing bioreactor. The Flushing bioreactor. He has worked on the design and engineering risk assessment of low-level radioactive waste repositories at DRIG, and was founding honorary editor of the ICE journal Waste and Resource Management, a member of scientific committee of the International Waste Working Group, chair of the Technologies Advisory Committee for DEFRA's £30 million program of research and demonstrator projects for new technologies for the treatment of biodegradable waste. And also, known to many of you, he's the author of a widely respected textbook, Soil Mechanics Concepts and Applications. So a very diverse spread of expertise there. So now, without further ado, to the topic, transportation infrastructure earthworks, resilience and sustainability, then, now and in the future. Over to you, William. Thank you.
Okay, thanks, John Paul, and hopefully everybody can see the slides and everybody can hear me. So thanks very much for the invitation, and thanks to all of you for joining in. So as John Paul has said, I'm going to talk about earthwork slopes for transportation infrastructure then, now and in the future. And I'm going to be talking about work that's been carried out over quite a long period of time by myself, but also my colleagues Joel Smethurst and Kevin Briggs. So I very much need to acknowledge their contribution, as well as that of various others, as will become apparent as we go on through. So I was going to say something about the nature of old infrastructure slopes, which goes back to how they were constructed, to then talk about the importance of wet winter pore water pressures. So those are really the pore water pressures during a wet winter is what's meant by that. The impacts of vegetation and the benefits of vegetation management, and then to say something about how we can stabilise these slopes using discrete piles, and that will be with reference to 3 case studies at Hildenborough, Mill Hill and Grange Hill. And then a few thoughts about modern and future earthworks before then making some concluding comments. So old infrastructure slopes are very often railway embankments. They're often well over 100, probably 150 years old. They're probably made of, the troublesome ones at least, are often made of clay fill, and that would have been fill that was won from a cutting fairly close along the line of the railway that was being constructed. They're often just end tipped, so they were never compacted or built in layers or anything like that. And they have hidden defects, which could include shear surfaces, high permeability lenses or regions. And they also have what we call a clodden matrix structure, which I will illustrate in just a couple of slides' time. So there's a couple of archive photos here which show end tipping of an embankment. So the railway is just being built along the embankment as we go, and then the material is being tipped off the end in wagons. And you can see there's been no real preparation of a foundation or anything like that, so that the embankment's just being built literally on a green field. And there's another view there from the end, so we can see the embankment progressing. And it looks as if that trees, roads, or anything that was in the way just got buried. So there wasn't really any attempt to build a foundation for that embankment. Now, very often the material that had been excavated is dug up in clods. So the structure of the matrix often comprises, so the structure of the embankment often comprises these reasonably sort of intact lumps of clay, pretty much as dug up. But then over time, that can sort of soften and swell at the edges. So you end up with the lumps of intact clay sitting in a kind of sea of what we sometimes call matrix material, which is generally softer and possibly wetter. It can act as a conduit for fluid flow. So that can be a sort of high permeability zone, and also tree roots will tend to preferentially penetrate through the softer matrix material. I think this terminology was first developed by Tony O'Brien from Mott MacDonald. So this is just an electron micrograph, basically, of a lump of clay fill embankment, and the way that it works is that the lighter regions are denser. So it shows these sort of clods and the clods. So the clods are the sort of grey regions here, like D. The matrix infill is the material such as C. So all of those dark zones. B is actually a hollow stone, interestingly. So the dark bit inside, the black bit inside, is actually a void inside a solid stone, which is otherwise quite dense. So this structure doesn't necessarily show to the naked eye. To the naked eye, you might see some of the bigger cracks, such as we've got at the bottom here, but a lot of the smaller ones are not discernible by the naked eye. So that makes some sampling and characterization of the material quite difficult. So that's my colleague Ian Sinclair, who operates the big scanning machine, which is used to investigate the structure using CT scanning. So it's reasonably well known. So work's been done at Imperial College and elsewhere, looking at the progressive failure and deep-seated slips. So this is a sort of classic slope failure, that an embankment slope or a cutting slope, which is over steep, can develop a what's sometimes called progressive failure, because what happens is where the clay material exhibits a peak strength, some of it becomes overstressed, and as the material continues to strain, it loses strength, and that means that it sheds load onto adjacent bits of material. So that over a period of years, with small movements, we can see that a slip surface will gradually progress until eventually we've reduced the strength because we're beyond the peak across the whole of the rupture surface, and at that point you can begin to get a failure. So there's just a couple of pictures here from slips that have occurred on embankments. This is Stonegate, so you can probably sort of see the back scarp, as it were, of the part of the embankment that's remained intact. So that does look a little bit like a kind of the circular slip. And then this is another one, which was at Harbury between Leamington Spa and Banbury, which occurred in 2015. So this is during remedial works. And again, you can see the back scarp of the intact material. This was actually a cutting. So there's the back scarp of the intact material. And then the slip has occurred in this very, very deep cutting. This is from a trial pit, which is near the toe of an embankment in high plasticity clay. And again, we can see there is a failure surface, which could well be a sort of residual surface. Whether that's still active or not is not necessarily clear. So we end up with all of these internal flaws and structures within these clay fill embankments. So those sort of classic failures are reasonably well known. I think what is now better known than it was maybe 10 years ago is that with seasonal variations in weather patterns, but especially in the uptake and evapotranspiration of water by vegetation, what we see are potentially very significant variations in the water content of clay soils. So that this is some data from, it's actually a cutting in London clay on a road at Newbury for the Newbury bypass. It covers a period of about 5 years, but in fact, we've got about 15 years worth of continuous data on this site. And this shows the volumetric moisture content as a function of time measured by time domain reflectometry theta probes, and they're at different depths. And what we see is that with the shallow ones down at 0.3, then 0.45 and 0.6 meters depth, we get these cycles of seasonal drying during the summer and wetting during the winter. And then that reduces with depth. So at the deeper ones, 0.9 meters and 1 meter depth, we're not seeing too much of the effect at all. But certainly over the top meter or so of soil, and this was a grass covered slope, we're seeing generally very significant drying out in the summer, then wetting up in the winter. And then you can start to see that not all years are the same. So we had 4 years here where there was quite a significant drying out in the summer, but then a couple of years where the summer drying didn't really happen. So they were probably not particularly great summers back in 2007 and 2008. So the problem with that kind of shrinkage and swelling is that while it might not cause imminent collapse of the earthwork, it is a real operational nuisance. So there's a couple of pictures here. This one is on National Rail. This one is on a London Underground line. But the problem occurs when the permanent way engineers are trying to maintain the top of the railway when the embankment is shrinking and swelling below them. So even though it might not be an issue in terms of causing immediate failure, that seasonal shrinkage and swelling is very problematic. And certainly on the Wessex route down from Waterloo to Southampton, over the past few years, there have been summer speed restrictions as a result of seasonal drying out and disturbance to the top of the railway line. So it is very much a nuisance. But in fact, it can lead to a gradual or ratcheting failure of the slope. So these are a couple of slides from finite element analyses. And again, we see similar sort of effects in geotechnical centrifuge modelling. So there's quite a lot of literature on this. This is not my own work. This is some work by Mott MacDonald, with whom we were working at the time. But these are the sort of typical shrinkage movements during the summer. So during the summer, we tend to get predominantly downward movement with a very small lateral component inward. But then in the winter, when the embankment wets up, it tends to move, it has a higher component of lateral movement, so that the downslope movement in the winter is greater than the upslope movement in the summer. So we end up with this gradual sort of ratcheting of the slope potentially down the hill. And of course, in the summer, we tend to have low pore water pressures. In the winter, when the vegetation is not taking so much moisture out of the soil and the water content is higher, that's also associated with higher pore water pressures. And as we all know from soil mechanics, that means that it's quite damaging for the stability of the slope. So there is also the possibility that these elevated pore water pressures in the winter with the water table near the surface could trigger a slope failure, such as the ones that we saw on the earlier pictures. So the first piece of work that I'd really like to sort of go into in a bit more detail is some work that we did looking at the wet winter pore water pressures. And in some respects, just getting a handle, all of that long time series data from Newbury and from other sites is important, because you can begin to see what kind of variation do we get. And you realise that not all winters are equal. And the worst condition is where you don't get the drying out in the summer. So you would have, for example, a wet summer, a wet winter. Then if you have another wet summer and another wet winter, you start to get really quite onerous pore water pressures in the earthwork. So this is just a reminder, this is the Harbury failure, that high pore water pressures reduce the stability of the slope, so we can get the failure that we've seen here. And these are pore water pressures plotted against depth. So these were measured by Andrew Ridley in a number of London Underground embankments, and that was in the wet winter of 2000-2001. So there's a variety of different sites, and it's just the maximum recorded pore water pressure as a function of depth below the clay surface in basically clay London Underground embankments. And if you look at all of the data, it looks like a bit of a measles plot. But if you had to put a worst case through that, you would say, well, it's hydrostatic. So in fact, the London Underground sort of default pore water pressure conditions in an embankment in the winter is hydrostatic below groundwater table up at the surface. But it's worth looking at the data a little bit more closely. So obtaining contextual factors, so looking at things like what is the fill made of, what is the foundation material, and even down to the slope and the orientation and the slope angle, and so on, we can start to get a little bit more richness out of the data. So the most important one was the effect of the boundary condition at the base of the embankment. So if the embankment was on London clay, then indeed we did generally get pretty high pore water pressures in the winter. So the hydrostatic line from the surface is the one which is dotted. The sort of worst case scenario would be perhaps this bilinear distribution, and most of those measured pore water pressures where the foundations on London clay are actually getting up towards the boundary. But if we now separate out the embankments on a chalk or a gravel foundation, which is much more highly permeable than the clay embankment, therefore allowing the possibility potentially of downward drainage into the chalk foundation, we see that those pore water pressures are generally very much lower. So in fact, the influence of the foundation of the embankment is very significant. So to investigate that a little bit more, we carried out some simple analysis. It's just one-dimensional flow, but it does do unsaturated flow. It was using the program VADOS W, so we didn't have any components of cross flow, and we were just looking at where would the pore water pressures get to as a result of rainfall and evapotranspiration associated with grass applied after an initialization period for measured weather patterns for 2000 and 2001. So we applied that, the rainfall and the evapotranspiration at the top of the columns. That represents a 1 in 100 year wet winter with that data. And we looked at some different scenarios, and what the question was is where do we get to with the winter pore water pressures in this case? And it's as if we're looking at a vertical here through a point about halfway down the embankment. Now, model A had got a high permeability surface clay fill, and that represents the effects of desiccation, for example, which does seem to be the case. It's difficult to model what you measure in reality without having a high permeability surface layer. So all of the models had a high permeability surface layer. In model A, the 4 meter high representative embankment was made of fill of permeability 5 times 10 to the minus 8 meters per second, and in model A that was sitting on a well-drained foundation, so a foundation of chalk or gravel with a permeability 3 orders of magnitude greater than the fill of 5 times 10 to the minus 5. Model B was the same, except it was sitting on a London clay foundation, so the permeability of the foundation was 5 times 10 to the minus 9 meters per second, and model C had got both the embankment made of low permeability clay as well as the foundation, both at 5 times 10 to the minus 9. And then the line of zero pore water pressure was 2 meters below what was considered to be original ground level. So the VADOS model was run. And then at the end of that, we can see that the wet winter pore water pressures in model A, which is the underdrained embankment, generally are fairly close to zero, except perhaps over the top couple of meters. Model B, which is the embankment founded on clay, is indeed fairly close to hydrostatic. But interestingly, model C, which is the low permeability embankment, it's such a low permeability that nothing really very much happens. So the precipitation in the winter never really actually penetrates into the body of the embankment. So that is also good. So in many respects, what this shows is that the worst thing that we can really have is a sort of intermediate permeability embankment on a low permeability foundation. If we can give the embankment a high permeability foundation, so it's underdrained, or we can make the embankment really solid so that it's well compacted and of low permeability. That is also a good thing for controlling the wet winter pore water pressures. How does that compare with the data? So we've just replotted the data here, and again, this is Andrew Ridley's data. So these are the slopes with the London Clay Foundation with the result of the model, which represents an upper bound, maybe not the best upper bound. And then these are the results of the chalk foundation, which again are a bit higher than the model, but generally we can see that we're explaining the right kind of trends with that simple model. So in summary, what we've seen is that pore water pressures can remain low in embankments underdrained by a chalk or gravel foundation, even during an extreme wet winter. That was a 1 in 100 year winter that we looked at. That a fill of permeability 5 times 10 to the 9 meters per second or less will prevent rainfall from entering. And again, the pore water pressures remain low. And the worst thing is really a fill of permeability, which is 5 times 10 to the minus 8 meters per second or higher on a low permeability foundation, which will give us the generation of near hydrostatic pore pressures during an extreme winter. So the paper that I mentioned actually explores a wider range of scenarios than that, but that's, I think, the key message. Okay, next topic is the effect of trees. And again, there's a couple of papers there where some of this work has now been published. So trees are, on the one hand, good because they can keep winter pore pressures low. The previous one that we were looking at was just a grass or shrub covered embankment. So these are some, again, numerical results, and the hatched areas are zones of suction, which remain even at the end of a wet winter with trees present. So those zones of suction, suction in excess of 200 kilopascals, in fact, are obviously going to be doing quite a lot in terms of helping keep the embankment stable. But again, the problem with trees is that they do exacerbate the shrink swell movements, which are such an operational nuisance, as we talked about earlier on. So I've just got a few bits of data to share from an experiment which was carried out by Network Rail at an embankment called Magnolia Road in Southend. So it is quite interesting to see that there's the underlying clay fill, the embankment fill here, and how much that has settled over the years and had to be topped up with ash, as we can see from here. So in this location, we installed a number of inclinometers to look at downward movement of the slopes. We had a number of extensometers, so we could look at the settlement or the heave at different depths. We had some of Andrew Ridley's geopiezometers, so again we did this work in collaboration with Andrew Ridley, and we also had some neutron probe access tubes. So the neutron probe basically we used to measure the volumetric moisture content of the soil, and we also had some conventional standpipe piezometers. So after an initial period of monitoring, the trees were removed from the embankment, and this is actually quite a draconian tree removal. They've pretty much all gone. So that's the embankment, and you can see there some evidence of trees having been cut down along with some of the instrumentation that was installed. So the embankment was originally covered in mature trees, so we can get a feeling for the extent of the vegetation as in the picture at the back. It's generally fairly low annual average rainfall, being in Essex. Some of the trees were removed in March 2007, and then they were all removed in March 2010. So if we look at the heave of the embankment measured by the magnet extensometers, for the initial period, what we're seeing is that over the summer, so this is getting into July, September, we see that the embankment settles, and the settlement measured up at the surface actually reached 40 millimeters here. So that's at a depth of 1.14 meters. And then with increasing depth, the settlement reduces. The orange line here is at a depth of 7.6 meters, where not much happened. So what happens is that the summer comes along, the trees extract water from the soil, and then in the winter, the soil wets up. And at this point, we would normally expect the cycle to repeat itself and we would get another summer dip, but the trees had been removed. So what happened was that instead of the shrinkage, we saw a swelling, as evidenced by the extensometer devices. The swelling increased and then it seemed to stabilize, but then it continued again, and then we're back to some cycles, possibly as the vegetation reestablishes itself. So the effect of taking out the trees means that, yeah, we have sort of taken out these annual cycles of shrinkage. But on the other hand, we've got a long-term swelling. And of course, this long-term swelling is going to be associated with an increase in water content and hence of pore water pressure. And that's affecting a depth down to something like 3.5, 4 meters, if we look at the data over on the far right. So the neutron probes enabled us to measure the volumetric water content with depth. And it started off down here with this bottom line there, that sort of orange one. And then once the trees had been removed, we could see the embankment fill here wetting up from the surface with typical moisture content versus depth profiles coming like that, and then moving across here, and then gradually the wetting up profile increased in depth down to the bottom of the fill at a depth of 4 meters. So there is no doubt that the removal of the trees was associated with a gradual rise in the equilibrium water content, and therefore also in the pore water pressures of the embankment fill. Now, tree removal is true draconian. If we think back to the previous example that we had, this is the Hawkwell embankment, the South End embankment, at the end of the experimental period, where we've just left a few trees here, and that is the zone of suction. And previously we had a very big zone of suction over both sides of the embankment. Now, there's just 3 pictures here which show, first of all, the bottom right, which is number C. This is the embankment covered in trees, which are shown in red. So the white zone here is the zone of suction at the end of a wet winter. So with trees covering the whole embankment, we've got a large zone of suctions remaining at the end of the winter. If we take the trees away so that we only have grass and let it come into equilibrium, we see that we've lost all suction. But if we leave the trees on at the bottom, then we have still got a zone of suction at the bottom, at the toe of the embankment left at the end of the winter. And that probably looks like a reasonable way of managing the vegetation, if that can be done, because it means that we've got the trees away from the railway line and they have taken out the worst of the shrink swell, but they're still giving us a degree of wet winter suctions, which will help with the stability of the slope. So the messages there are that modest, controlled grass or small shrub type vegetation on slopes is a good thing because it lowers winter pore water pressures. The roots may also have a binding effect, but we've not looked at that in this work. And then secondly, that high water demand tree species need to be avoided, especially within 1.5 times the tree height of the railway. The trouble is that often puts them outside railway land and beyond the control of the infrastructure owner. So trees do remain a problem, not least because they tend to fall on the track and trains can run into them. But vegetation management does seem to be quite key to controlling pore water pressures in those slopes. Okay, so the next topic is going to be on slope stabilization using discrete piles. So we can try to stabilize infrastructure slopes using a variety of methods. So sometimes we might put in a complete contiguous or continuous retaining wall. We might try a softer solution such as nailing or lime stabilization, but spaced discrete piles is a sort of intermediate solution. And what I mean by that is that we put these piles in usually about midway down the slope. And the idea is that they're far enough apart that they're not continuous, but they're close enough together that we don't get flow through of soil in between the piles. So we got a number of sites where we'd monitored pile stabilization schemes to try to sort of shed some light on a number of unknowns. Typically, our instrumentation would have consisted of strain gauges inside the piles, so we can measure the bending moments, inclinometers inside the piles, so we can pick up pile movements, and also inclinometers in the soil, either between the piles, so we can see how much that is moving, or possibly upslope or downslope. In addition to that, we would try and have piezometers and a rain gauge, so we can look at the influence of weather and of vegetation on what's going on as well. So there were a number of uncertainties about these discrete piles over the mechanisms of behaviour and the appropriate method of analysis, especially when they're installed in slopes where there might not be an obvious failure surface. There are other questions such as how far apart do they need to be and where in the slope and what sort of depth they need to be, what bending strength and what stiffness. I'm not really going to cover those last 3 bullets very much in this talk. So the field studies that we have got are the particular ones on the pile stabilisation are at Grange Hill, Mill Hill and Hildenborough. I've talked about Magnolia Road, which is the one at Southend. That was the vegetation, the tree removal experiment, and I've also mentioned Newbury. So those are some of the sites that we look after in the southeast of England. So these are the three sites that we're going to talk about with the pile stabilisation. There's an embankment at Hildenborough in Kent, which is in wheeled clay. There's another embankment at Mill Hill, which is in Anglian Till, and that's on London Underground. And then there's a slope at Grange Hill in London Clay, and that's on the Central Line. So Hildenborough had ongoing problems with track geometry, and the approach there was to install discrete piles, but also a layer of rock fill on the surface of the slope. And our instrumentation included inclinometers to monitor slope and pile movements, strain gauges to monitor pile bending moments. So this was the proposed remediation. This is the slope geometry during pile installation. So they cut back the original slope. So it's basically wheeled clay on weathered wheeled clay and intact wheeled clay. So the piling platform was built out of imported rock fill. The piles were installed, and that's a picture up there top right during pile installation. So that's just a bigger view of that picture. So you can see there the piling platform. Those are our inclinometers, which are protected by those casings to stop them being knocked over. And then eventually the slope was regraded, so there's this quite substantial rock fill cover with the stabilizing piles in here, and that's shown in this picture here. And again, that is a close-up view or a zoom out view showing the instrumentation with the piles and the instrument cabin, and you can see there the rock fill is quite clear. So that's just another view showing the instrumentation. So there's the inclinometer tubes in the piles with the strain gauges, inclinometers in between the piles, and then there's the instrument cabin. That's just a close-up of the strain gauge fixed to the reinforcement cage. So we're not going to look at the bending moments, we're just going to look at some of the movements. And what this shows is the movement of the slope. So these black ones here are the tube between piles A and B shortly after installation. The open symbols are the two tubes so this is in the slope between the piles, and this is after about 3 years. So we can see that actually the piles haven't stopped the movement completely, although it is an awful lot less than it was, and we're beginning to see this is the kind of movement of the slopes that we're getting. These are the corresponding pile movements. So again, we can see the piles are actually moving a fair bit, about 5 millimeters after 42 days, up to 35 millimeters here. So those are the deflected profiles with depth of the 3 piles in the short term and the long term. The interesting thing to look at is what is the relative movement between the piles and the soil. So if we take a couple of examples at the early stage, day 42, we've got the pile in the solid symbols and the soil in the open symbols. And then after 3 years, we've got the same, the pile in the solid symbols, the soil in the open symbols. And what's interesting is that up at the top here, we can see the pile is actually moving further than the soil. But remember that this upper layer of soil is rock fill, which is all pretty stiff. So this is telling us the relative patterns of pile and slope movement, which are that the pile's moving more than the soil up at the top, then it swaps over, and then it swaps over again. And that all seems to be rather odd. And it's actually confirmed, though, by the inferred net lateral pressures, which can be obtained by differentiating the appropriate number of times the bending moments from the strain gauges or a spline fitted to the measured displacements. And then that seems to show that we've got upslope pressure, downslope pressure, upslope pressure, downslope pressure. And again, that seems to be slightly unusual. But if we think about a sort of mechanism of behaviour, even though a slip surface might not have fully formed, maybe that gives us a clue as to how the movements are occurring. So if we think about the movements associated with rotation of this mass of soil about a fixed point here, so basically for a given angle of rotation, the movements are going to be perpendicular to the radius and proportional to the distance from the radius. So along a vertical line that might represent the pile, we can pick up this sort of expected pattern of soil movement associated with the development of a rotational pattern there. But the pile, if it's stiff, is going to essentially rotate about a point near the toe. So the pile is going to do something like that. And what that does tell us is that because of the stiffness of the pile, we probably will get the pile moving further than the soil up at the top. Then it swaps over, then it swaps over, then it swaps over. So that would give us this, thinking about the mechanisms, would give us this pattern of upslope, downslope pressures on the pile. And that actually does match what we picked up from the measured displacements and bending moments. So the next case study is Mill Hill East. So this is the Anglian till embankment. So this is the works going on. You can see probably there the line of piles. They're fairly closely spaced, and that is the London Underground line running on the top. And so here we had got 11-metre long stabilising piles. The foundation was London clay, reasonably slope of 20-24 degrees, probably looks quite steep when you're on site. And then this is the piling platform for the installation of the piles. So that's the cross section through the embankment. This again is just another view showing the instrumentation. So inclinometer tubes and piezometers. 2 piles have got strain gauges and an inclinometer tube within the piles. We'd also got piezometers and moisture content measurement and inclinometers in the slope. But again, I'm really just going to focus on the relative pattern of soil and pile displacement. So this is what the site looked like after the instrumentation had been installed and it had been tidied up. So initially, we'll just look at one pile. This is pile C. So initially, it actually apparently moved back into the embankment. So it started off here, it moved back into the embankment, and then it started to move down slope. And the soil in front of the pile behaved itself possibly a little bit better. It just gradually moved down slopes. This movement of the pile back into the embankment was apparently quite curious, but in the end it looked like that was associated with a general removal of water from the embankment by the vegetation. You'll notice it's still covered in trees, so that was probably a general shrinkage inward of the embankment before the pile really started to function as expected. So we can confirm that by just looking at the pile. So the pile has clearly gone back into the embankment. This is the soil displacement behind the pile, which again has generally shrunk backwards into the embankment. And then the soil, once we get onto the slope, has started to perhaps move down slope again like that. And then after a period of 5 years, things are behaving more as we would expect, with the pile tending to bend down slope, but only a displacement of 4 or 5 millimetres. The soil displacement behind the pile, again moving down slope, but generally by less, and the soil displacement in front of the pile moving down slope, but generally by more. So again, if we look at the net pressures from a spline fit to the displacements, that tends to tell us that actually in both cases we have got downslope pressure, upslope pressure, downslope pressure, and this is probably a result of the shrinkage of the embankment driving the behaviour. But then in the later times, we're getting perhaps a more expected downslope pressure, and then that's balanced by upslope pressure and downslope pressure at the bottom, where the pile is tending to bend downslope, rather than in this case, where the pile's actually been sort of pulled inslope by the general shrinkage of the embankment. So in terms of the relative pile soil movement, we can sort of idealize the relative movement like this. This is the early times where we have got the general pulling inwards of the embankment, and then the pile has to deflect like this. So we've got relative movements such that the soil here, even though it's all moved inwards, the soil is relatively outwards compared with the pile. Then it's inwards, outwards and inwards. And then at longer times where the general sort of expected downslope movement of the soil has kicked in down to a depth of about 2.5 meters. The soil's wanting to do this, it's pushing the pile with it, and the pile is then embedded into the more stable soil at depth and it's resisting it. So again, those are the sort of cartoon mechanisms of the two different types of behaviour that we have. So interestingly, the early behaviour driven by the general inward shrinkage of the embankment induced by the removal of water by the vegetation. So if we think about the sorts of pressure diagrams that we would expect from these idealized patterns of relative displacement, we can see that they do conform to the sort of thing that we measured. So that's the inward shrinkage, giving us a slightly more complicated pattern of loading than the longer term, which is where we've got the downward movement of the soil being resisted by the pile. So we've got downward pressure, upward pressure, and then the pile being sort of embedded in. So the initial movements of the piles seem to occur due to seasonal shrinkage of the clay film. The later pile movements are associated with generally shallow downslope surface movements, but we do still notice small seasonal reversals in pile movement and bending moment. And generally, the pile movements have remained small. Okay, the last one is Grange Hill. So this was a cutting. So that was it prior to the remediation works, and it was adjudged to have a low factor of safety. Interestingly, just on one side, because there's a cross flow of groundwater here. So the pore water pressures were much higher on one side of the cutting, this side of the cutting, than on the other side. So it's an 11-metre deep cutting, and it was adjudged to have a low factor of safety. So this was stabilised by discrete piles inserted again at about mid-depth of the cutting. So this is a photograph during the installation of the piles, and you can see the other side hasn't really had to be remediated. This is a photograph after remediation, so some trees have been allowed to remain, but generally it's a fairly clear cutting. So in this case, we have got 2 dates for the displacement of the pile, which is shown in solid, and this is an average of the piles, of 2 piles. So this is the short-term movement, fairly shortly after installation, the April one, and then 2 years later, or 2.5 years later, the pile has moved to here, and the soil midway between the 2 piles has, as we might expect, moved a bit further than the pile, and actually the relative movement of both of those is quite similar in both cases. It's just there's been generally more movement in the case of the later date. So in this case, this scheme is probably behaving as we would expect. There is a general downslope of the upper few meters of soil, so we would expect the soil to be doing something like this. It's not associated with a developing or almost developed slip circle like Hildenborough was. It's more of a sort of gentle downslope movement, so we would expect the soil to be doing something like that. The pile bends being built in, and so we end up with downslope pressures on the pile being resisted by upslope pressures on the pile, and that is the sort of thing that we have monitored. So in this case, there is no distinct slip surface, and it's interesting to speculate that perhaps the piles have been successful in preventing that. Now, the last sort of summary slide shows the rates of pile movement and the total accumulated downslope movement. So this is actually now a couple of years ago, but Hildenborough, they are still moving. So we haven't stopped, things haven't been stopped completely. And that's going to play into something that I'll probably just say in the sort of concluding or the last bit of the talk. People like to think that we can build something that won't ever need maintaining, and I don't really think that's a realistic ambition. So I think that continued management of the vegetation and attention to maybe minor slips is probably something that we have to expect to do with earthworks, but of course it's not what people try to do. Okay, so modern and future earthworks. So how can we overcome these problems of continued movements, of shrinkage and swelling and so on? So there's a number of things that we can do, but each of the things that we might do comes with a cost. So we could use high quality fill for at least for the embankment core. But then we find that we start to incur environmental and other costs, cash costs and environmental costs, in obtaining this high quality fill. We also have to transport it. And if we're not going to use material that we've excavated from along the line, we then have to dispose of that. Now, we can dispose of it in a landscaping berm, which is maybe not a bad thing to do, but it means that the land take during construction is really quite considerable. And so you end up with that disruption until it's all returned to agriculture. So using high quality fill for at least the structural core of the embankment, perhaps lower quality material for the shoulders, and then for some sort of landscaping is a possibility. But we quite rapidly get into very, very significant movements of earth for both disposal and import. And we also quite rapidly get into a huge requirement for high quality fill. And that's before we even take into account of trying to obtain material for the concrete. We can have shallower slopes. And again, the downside of those is that there will be a much increased land take, at least temporarily. But if they could be so shallow that maybe they could be returned to agriculture, then provided we're not sort of demolishing ancient woodland or something, that might be a thing to do. But of course, there's going to be a cost involved with it. We could try to have minimal or bespoke vegetation, but then the vegetation is going to require active management. And as I just alluded to, there's probably no real way around that. Good drainage, I think, is for a modern geotechnical engineer, almost goes without saying. But again, it has to be constructed. We might need to think about active maintenance, and we do need to think about all of that. And also good construction. So, for example, making sure that we compact everything and we have sound foundations. So I think the last two bullet points probably don't particularly incur any huge cost. It's what we would now do as a matter of good practice. And one hope that I've showed, certainly with the work on wet winter poor water pressures, is that good construction, making something of low permeability and good drainage so that the water has somewhere to go, do pay dividends in terms of the stability of the construction. Vegetation management is an interesting one, because I think it's to stop self-rooted trees and things like that. You're probably always going to have to have some kind of active vegetation management, and the longer you leave that before it gets out of control, the more difficult it's going to be to put it all back together. So I think we know what to do, and I think at the moment we're probably trying to find a balance between how much of this do we do, how much do we put onto capital costs versus ongoing maintenance. Is ongoing maintenance such a bad thing? And very often we perhaps don't think up front about the environmental cost, by which I mean the number of lorry movements that we might need to make in order to import and then import good fill and dispose of unsuitable fill, and the number of quarries that we tie up and the amount of material that we use in order to win the good quality fill. And those actually do start to pose a challenge on a major infrastructure project. So, by way of concluding comments, to summarise really what I've said, I think estimating wet winter poor water pressures in embankments requires us to consider both the lower drainage boundary conditions, for example, is it on a chalk or a clay foundation or a gravel foundation, and the embankment permeability. Vegetation can be managed to realise benefits of lower winter poor water pressures without the nuisance of excessive seasonal shrink swell. When we use discrete piles to stabilise the embankment, the pile pressures depend on the relative soil pile movement, and that is consistent with simple mechanisms of slope and pile displacement associated with combinations of a deep-seated slip, which was the case of Hildenborough, shallow downslope movement, which was the case at Mill Hill in the long term, and Grange Hill, and also inward shrinkage due to vegetation effects, which we saw in the short term at Mill Hill. The upslope pressures on the upper part of the pile may occur if we've got a stiff stratum. So I suspect that had it not been for the rock fill, we probably wouldn't have seen that at Hildenborough. I think the stiffness of the rock fill was quite important in that respect, or as a result of the inward shrinkage due to vegetation effects. And then finally, modern methods of design and construction can avoid many of these problems, but we do need to think about, are they financially viable, especially if we try to front load construction costs so that we have a maintenance-free transport corridor. And we also do need to think about the environmental implications in terms of the use of material, the disposal of material, not just the fact of the material itself, but also the movements, the transport costs of doing all of that. So I think I'm going to leave the slides with you. It will be recorded, but this is some of the work has been written up in some of these papers. And in addition to the co-authors at the front, I should acknowledge funders EPSRC, Andrew Ridley's Geo Observations, Highways Agency and Network Rail, TfL, Tube Lines, Metronet and Mott MacDonald, who've all collaborated with this. Other than that, thank you all for listening, and hopefully we've got a bit of time for questions.
Okay. Well, thank you for that wonderful exposition with many case histories of tremendous interest to us all. And we do have several questions, mostly from Phil Wilson, in fact, but I would like to sort of if possible, divide up some of his questions with some from anyone else or possibly myself. In the first question that I'm going to ask, it's from Phil Wilson, as I said. Any view on whether vegetation versus structural type spaced pile is the best solution in terms of cost, sustainability and effectiveness? Now, I know that this was pretty much what you were talking about in your summary, and so he's inviting you to expand a little bit on your ideas there.
So I think the answer is that it probably depends whether you're remediating an old earthwork or whether you're building new. I mean, I think if you were building new, you would probably go for a decent slope, good drainage, good compaction and controlled vegetation. If you're remediating something, then there would probably be factors to take into account. So, you know, as I mentioned, trees are a bit of a nuisance because they do tend to fall on trains or in front of trains. So I think you would definitely want to try to keep the transport corridor reasonably clear, whatever you did. In the case of Mill Hill, leaving the trees in place was part of the solution. In the case of Grange Hill, it obviously wasn't. So I think that part of the rationale for that is that Mill Hill was an embankment, and if a tree falls down, certainly if it's away from the top, it's probably not going to endanger the railway. At at Grange Hill, it was a cutting. Again, you know, trees are not free. Once a tree gets to a certain height, it has a certain weight, it does need to be maintained, and tree maintenance is quite expensive. The discrete piles, I think, can be done much more economically than many people currently do it. So you can expand that spacing to probably at least 3, maybe 4 pile diameters. With MOTS, we kind of settled on 3 pile diameter spacing, but I think a lot of people are still installing them more or less continuously. So I would look at, I think you might want to do vegetation management for other reasons. So I think there's no hard and fast answer. It kind of depends what you've got. It depends on the circumstances, but very often a combination of the two is probably going to be the right approach, certainly with dealing with a historic problem.
Okay, so I had a question to put in here. In the Hildenborough example, this was a remediation for a slip surface. Very nice sort of double reversal in the cross section and explanation. Did you actually intersect and find the location of the slip surface, or was this, I mean, analysed without actually knowing where it was?
Yeah, so my view is that it wasn't a fully developed slip surface, but it was probably close to it, so that the pattern of movements had kind of started to get to that sort of pattern. But generally, you would want to try. You would need to put the pile in below, and the calculations that you would carry out, you'd make sure that you put the pile in below certainly the slip surface that would happen in the absence of piles. Obviously, what then happens is you end up with a slip surface which is deeper, but hopefully has a higher factor of safety from an engineering point of view. So it's conjectural, but it does fit. So the idea is that with small movements, it would be the sort of shallow downslope surface ones. But then as you start, as the mechanism starts to sort of develop, but before it has fully developed, you start to get the circular pattern, which I use to try to explain the Hildenborough pressures.
Okay, and another one, I just noticed the remediation in Grange Hill was obviously rather a manicured sort of look, and with the one sort of prominent tree. The question then sort of in my mind is with the sort of the direction going in that of encouraging biodiversity, certainly for new schemes, and this concern about the trees getting too out of control and large. There really is there a way in which in a modern thinking that biodiversity is beginning to trump some of these sort of geotechnical constraints, and that actually to manage a sort of rather unmanicured landscape is actually being encouraged? Can you comment on that?
Yeah, so I'm pretty sure Grange Hill isn't still like that.
Sure.
Newbury was interesting because Newbury was a cutting on the A34, and when we first started monitoring that, that was pretty soon after the Newbury bypass had opened. And when you look at photographs then and photographs now, you realise how the vegetation has grown up. So the vegetation will just grow unless you do something.
Yeah, sure.
But your question was really about the biodiversity. So there was a thing called the Varley report, which was a sort of report into actually Network Rail's management of its corridors, because they started to try to manage the vegetation, sort of felling trees and so on. And of course, local residents got up in arms, partly because the trees had provided a nice screen for them, so they didn't have to see the railway. And of course, the biodiversity issue was raised. And it did cause quite a lot of emotive response in the rail industry. And there'll be quite a few people, rail industry commentators, who say, come on, we're trying to run a railway here. We're not trying to manage biodiversity. The other side of that is that I think that if you're building a railway, especially building a new one, it goes through communities, and the communities get the disruption, even though, in my opinion, it's rather less than the disruption of a motorway. But they don't get the benefit because the train doesn't stop. There isn't a station. So I think, and again, we did some work for East West Rail, where you start to say, well, can we use the corridor for something else? So can you use it for things like active transport, walkways, cycleways, and that kind of thing? Can you use it for nature? So I would say that there is quite a strong movement in terms of planning for nature in a way that supports nature, and actually the green amenity, the green benefit is quite significant when it comes to planning and selling things to the community. But if you like, the engineer's role, working in collaboration with conservationists, ecologists and so on, is to make sure that the green amenity doesn't override the need to run a safe transport corridor. And I would like to think that that is the sort of enlightened way that we go forward, both in terms of vegetation management. So, for example, you can leave the trees near the bottom of the slope, but remove them from the top of the slope, and that way you can try to do both things. But it does require people to be willing to discuss it in an informed sort of way and move to a sensible solution, because you can't compromise the safety of the transport corridor.
Of course not. Yeah, that's a very interesting expansion on that theme. I've got a couple of quick ones before we must close, to do with technical issues. Actually, a suggestion. Phil Wilson was just wondering at the role of line modification for future earthworks. Is that something that you embrace?
So they did some trials of lime stabilization on London Underground, but I don't know what happened to it. I mean, lime will only really work with it's got to be it will only work with certain types of soil. I think the idea of some sort of zoned improvement, so whether it's lime, whether it's stone columns, I think is attractive because it should be reasonably economical and it's not too invasive. But we've never really, I don't think, managed to make it land. And I think it's because people are uncertain about, I think they're uncertain probably about, it's a very three-dimensional thing. You don't want to be treating everything, so you have a mix in place column or something like that. And I think people are uncertain how to quantify the benefits, and they're uncertain about the longevity. But it would be nice for some of those techniques to actually, for people to get a bit more confidence in them. So maybe what we need is some monitored trials. And as I say, I don't know what happened to the ones on London Underground, which were implemented probably 15, 20 years ago. Okay, and this last, I think this was asked right at the beginning before you'd actually got going, but I think it's a classic to finish, from Phil Wilson again. How do you reconcile positive benefits of vegetation for stability with disruption due to leaves on the line? And this is, is there a change in thinking to address the leaves on the line problem? So, I mean, there are various things that people have tried to do with leaves on the line. So from ultrasonics to sort of blasting it off with high pressure water, the sandite treatment and everything. But, I sort of think it isn't just leaves on the line. The incidences of trains hitting or trees falling onto railway lines has increased dramatically over the last 5 years. With increased storminess, one is going to see that. So I think, probably to reiterate, I think that some of the techniques we've looked at very much point towards removing vegetation from the immediate vicinity of the railway line, leaving it certainly on the toes of an embankment, less obvious with a cutting, and also, the need. So I would say remove it from the immediate vicinity of the corridor. And the other thing that I don't think we've ever done in our calculations is that trees actually weigh quite a lot. So there is an embankment which is covered in trees is going to be carrying quite a lot of weight. So we're uncertain how to take that into account. We're uncertain how to take into account the reinforcing effect of roots. But again, there are people working on that. I think it comes back to the point that we should try to make the transport corridor a green amenity, especially for people who are affected by it but don't benefit from it. But it can't be at the cost of compromising its safety. OK, well, look, William, that's tremendous. I think we're going to have to wrap up now and close the session. It's just turned 1 o'clock. And I'd like to really thank you for a wonderful presentation, giving us a real sort of insight with what people are grappling with in the future with HS2, climate change issues of changing weather, drying out and wet. And also, I'm aware of your tremendous work going on in developing these numerical models for a number of themes in terms of track ballast behavior and so on. So great to see you working on this, helping to provide guidance to the whole industry. And thank you for spending time with us and sharing all your technical and expert thoughts. OK, I'm afraid we can't all clap, but very, very kind appreciation from all of us here. And thanks for coming, and goodbye. And OK, thank you.
I'll just say to everyone else, of course, this is the last seminar of the series, but we'll be welcoming you back with a fresh season in spring. And that should be, we've already lined up our speakers, and that should be a very exciting, diverse, eclectic mix of speakers. So I look forward to seeing you all then. OK, so it's bye from us. Bye. OK.